now. Certainly have seen his work longer than that, but I had the opportunity to meet him about 15 years ago. Ivo Desmedt is one of the leading researchers in the area of cryptography. In the US, he was one of the co-founders of, I think it was the third academic center in the United States involved in information security research. He has been involved in starting programs in education at a number of other universities around the world, has an international reputation for his work in security, and is currently associated with two positions, one at the University College in London and the other at the RCIS in Japan. He was recently named as one of, I think, only 6.
No, more.
Is it more than that?
I think there are around 20 now.
Around 20. 6 recent ones.
Yes.
Of the
International Association for Cryptologic Research.
Right. Thank you. My memory of the acronym isn't so good, but it's a distinct honor to be named as a fellow of that group, and it's a distinct honor for us to welcome today Dr. Ivo Desmedt.
Thank you. So what I'm going to talk about today is 60 years of scientific research in cryptology, and basically it's going to be more a reflection. I'm not going to do a survey of what has happened, but I think that it's going to be a time where I want to look forward to the future. And so what I will do is I will start very, very, very briefly from the first years until today. And the very is important there. And after having done that, then I will say, what is actually cryptography? And the reason why I'm putting as a second issue instead of starting with that is that you will see that from the research which has been done over the last 60 years, that the definition of cryptography has changed. And then the next question is, do we really need cryptography? Or on the other end, are we basically neo-Luddites who basically say that technology is really bad and we need to protect ourselves against it? And then I'm going to focus on crypto, in particular the research aspects. I'm going to start with talking about what are the strengths of our modern research, and then I want the balance stock. So I'm not only going to say good things, I'm also going to say not so good things. And so I'm going to look at what are the shortcomings of our modern research. And then I think I'm looking forward to the future with saying, what should we actually study in the future, and starting today, and then conclude. So this is very brief, as I said. The paper by Shannon appeared in 1949, although it actually predates the papers on information theory, but they were not declassified, and so therefore he wasn't allowed to publish them. And so that's why you see them out of sync. So you see the paper on the proof of the one-time path being secured after his work appeared on information theory, although in fact it was the work that he did on trying to prove that the one-time path was secure that led him to information theory. And that paper appeared in October 1949. So a little bit more than 60 years ago. So then you see that for a long time there was almost no scientific papers that appeared. And in 1974 there was the paper by Gilbert, McWilliams, and Sloan. Some of you still remember Gus Simmons when he was active. And what he had done is basically go around and speak to people in coding theory and speak to people in combinatorics, saying, how can you make sure that when you get a message that you can guarantee that it came from the sender and hadn't been modified? And Gilbert, McWilliams, and Sloan were the first to actually solve that problem. And that happened in 1974. It's a paper which is very rarely cited, but I think it's quite important, and that's why I put it in the very, very short list. 1976 was the invention in the unclassified area of Diffie-Hellman, new directions in cryptography. Obviously, this is a very important paper. In 1978, I put a paper there by Rivest, but there's no Shamir and Edelman. There's Edelman, but no Shamir and Edelman. You would expect basically the RSA paper there. But the RSA paper is basically a realization of what Diffie and Hellman were looking at. I think that the paper by Rivest, Edelman, and their Tusos is actually more important in particularly when you look at long-term research. And what they actually were trying to do is that you have encrypted data on the file server, and you don't trust this file server, but you want to use it, and you want to basically be doing computations with encrypted data. They did very little on it, but they just had this idea of that which they called basically privacy homomorphism. And the problem was recently solved in 2009 by Gentry, and it was important enough to actually make the New York Times. So what we see is that the first paper was basically on the security of encryption, the second on the issue of authenticity, the third of working with encrypted data. So you start to see that if you're now wondering what the definition is of cryptography, it's not just the protection of privacy and the study of encryption. And other examples are Blakely and Shamir with the invention of secret sharing, Rabin, digital signatures and public key functions as intractable as factoring. And then there are other papers, which I'm not going to mention. From cryptanalytic viewpoint, the Lenstra-Lova's paper is very important because today, if you look at many attacks that happen, they actually use that as a tool, and that's why I list it. And Goldwasser-Micali, I list that because I view that paper as basically the real start for the research on proven security, although you could say that Rabin was first, but there are differences, as we will see later. And there are many, many dots, and I said it has clearly very brief the survey of what has happened. Today what we have seen is a big explosion of papers. And so even trying to do that in a few minutes, you will never be able to do a good job. And so I know that that's not the goal of my talk. So the goal of my talk is to look forward and say, what should we look at in the research on cryptography? And so the first thing then is the question is, what's actually cryptography? And I gave an informal definition, and I put definition between quotes because you cannot give an informal definition, in 2000 by trying to actually give a formal definition for what cryptography is, and I failed. But at least the definition is different than what you will find in, for example, Denning's book that appeared in 1982 and other the textbooks, that I think it's important to see that it's not just the study of encryption. So the way I view it is that cryptography is the science and study of the abstract security aspects of data against a malicious adversary. And the abstract is important, although it's between parentheses, to basically distinguish it from the computer security. And so cryptographic systems I view as being, and they are being and have been developed to protect some of these security aspects of the data, and cryptanalysis then is a study of methods used to break such crypto schemes. As you see, there's nowhere, it doesn't mention, it says security aspects. And so that means that basically where we are today, what we may view as a security issue might be different than what we were looking at 60 years ago. And so that's clear from the slides before. Privacy was the main issue. Authenticity is considered today more important. There are also papers that combine privacy, authenticity, and reliability. Anonymity is a more new problem that has been looked at, in particularly by Sham, so that's one of the dots which is actually there. So, and there might be other goals that we haven't realized. So if you look, for example, at Gilbert, McWilliams, and Sloan, you could say, how the heck did it come that for so long there was never a formal study done about authentication until only 1974. Now, some people actually have looked at the issue of, has there been other studies? And the answer is yes. And they go back to the Dark Ages, the Middle Ages. But it wasn't in the mathematical sense of the word. But people had thought about it. And the fact that you have a document to which then you're going to basically attach a seal by basically putting some ribbon through it, making a hole or two holes actually, and then put a ribbon through, and then actually put a seal on top, implied that the seal, making a fake seal at that time was much more expensive than actually making a fake document. So people had thought about it before. It's not that they never looked at these things as some people claim. So what I'm now going to look at is, do we really need crypto? And there are many, many different answers. And so from a scientific viewpoint, one could say that cryptography poses challenging questions worth studying from an abstract viewpoint. Okay? So it's basically, it says scientific viewpoint, it says from an abstract viewpoint, etc. The question then is, do we actually write that in our proposals to obtain funding? And the answer is no, we don't. So what we actually claim is we claim that our area is applied and applicable. And so I spoke about that with Safa Finani, who some of you know, and she basically, her reply was that if we say research in an area may be largely driven by practical need or intellectual curiosity, then it seems to me that recent research in modern cryptography has been primarily of the second type. I'm not saying that's bad, but we also have to take into account what it implies. So back to the question, is there a need for practical cryptography? So Andrew Lisko in 2003, I remember Andrew Lisko going around and saying, you know, this small company, he mentioned the name small company, just went bust because they were not thinking about information security. And he said, it's just a question of time before a large major corporation is going to go bust because they haven't taken information security into account. And then it didn't happen. And so basically, he started to change his mind. And so in 2003, he said that the really massive financial disasters of the last few years, I mean, now in 2010, you could say the same, but the companies have changed, okay? At that time, it was Enron, long-term capital management, WorldCom, owed nothing to inadequacy of information security systems. How can we explain this? So, is SSH not a great application of cryptography? Yeah, that's what we say. But where is the hard evidence? In particularly, how do we know this? So, even if you put intrusion detection in place, and then you say, okay, somebody tried to get into the system and SSH prevented that, how can you calculate the estimated economic saving? There is no figure of that. I mean, there are people who basically throw a figure and say, this virus costed the world so much money, but it's basically throwing a figure. And there is not hard evidence. And in particular, when you look something as cryptography and SSH, how much has it saved? And so, and I had some chat with Andrew Lisko recently, who said that if cryptography wouldn't have been there, then if you look even at SSL, people would have found other ways to make sure that the transactions are, e-commerce transactions are not too bad, that the security of them wouldn't be too bad. So and then evidently there is answer 2 from Gene Spafford, who stated using encryption on the internet is the equivalent of arranging an armored car to deliver credit card information from someone living in a cardboard box to someone living on a park bench. Many people have actually not understood that statement. The statement says that basically, if you focus on communication security, but you don't have on both sides, that where you have this cardboard box and the park bench, you have insecure computers. Now, what is it good for to have all the security on the communication aspect? So, and I think that he's right. So then the question is there absolutely no positive reply to the question, what's cryptography good for? And so I'm going to look to a statement that I made in 2006. And based on that, I'm going to try to answer the question. So I think that research may predict potentially new frauds, and it may propose solutions against these. So what I think is that if you look in the area, researchers are ahead. The hackers, they actually usually catch up with scientists. However, not immediately. It makes them several years, actually. So business avoids really to implement security as long as economically justifiable, even sometimes longer. And they try to avoid taking the responsibility. And so then people say the solution should be the government is going to basically mandate information security. But even what happens is that today, as we know, the government is owned by the lobbyists. But if you push hard enough, the government will make enact regulation, but that needs to be enough pressure. So that's basically my background statement. And then the answer that I gave is that the deployment of cryptography is often a reactive action and not proactive. And this is due to an acceptable high level of hacking or due to regulations. It's not just something that people do just in order to be more secure, it is for economic reasons. And well-known examples are the use of encryption by the petrol industry for geological data after it became clear competition might have been eavesdropping on it and basically saved a lot of money because geological exploration is quite expensive. And this is from the Hellman's paper. the deployment of SSH around 2000, when too many telnet sessions were being sniffed, the requirement by credit card companies to use SSL for e-commerce, and the introduction of pin and chip in the UK when credit card fraud became too big. So that's all reactive. Are there cases where we can clearly show that people should have been thinking proactively? I think so. And so what I would like to add to that is that those that do not take information security into account should realize that they could burn their fingers. And there's a nice example that basically come to mind, and this is a potential example. I'm not saying that this is the real story, and that's AIS. Now, most of you who basically are familiar with crypto, you know AES. That's a block cipher. No, this is AIS. What is AIS? It basically allows you to find the position of ships. And so this is a web page called AIS Live. And what you see in there is that you can actually do a request for a 2-week free trial. Okay? And what does it give you? And this is actually from a different web page. It gives you live tracking of the ship locations. In particularly, when you look around Somalia, you can actually see where the ships are located. And so the Sunday Times, which is a British newspaper, November 23rd, 2008, made the following statement. It's also shockingly simple for anyone to track vessels online or to tune into ships' AIS beacons. So automatic identification system, that's what AIS stands for. They transmit a ship's exact position, size, and cargo. So if the Sunday Times is correct, the cost of lack of privacy in this technology is in ransoms alone estimated at 40 million. That was at that time, so it may have even increased. So what you clearly see is that the people who designed it completely ignored the information security aspects of it, completely ignored all the basic things as the need to know. I mean, why the heck do I need to know where all the ships are in the world? Okay? And then not only that, I can get a free trial for 2 weeks. Okay? So it's clearly, you should think proactively. Unfortunately, often it's not done, and here is yet another example. So, is Odlisco correct when pointing out that no major disaster has happened due to lack of information security systems? My reply that I usually like to give, and also to Ros Anderson, who says, forget about critical infrastructure protection, that attack, it will never be attacked, is that we had no major meteor hit Earth since the discovery of computers. The last one was in 1908 in Siberia. So I'm talking about electronic computers. So, but we know we will get one, okay? And so the way that these catastrophes are analyzed by people trying to analyze them is that they have a high impact. So the cost is quite high, but the probability is very low. And those of you who remember your calculus, if you have two functions, one tending to 0, which is the probability, and the cost tending to infinity, and you multiply them, what's the answer? Oops, it depends on the functions. It's quite interesting because what happens is you have functions that we actually don't know what they are because they're events that occur very, 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 very rarely. So even trying to make a model for them, we're going to be off, okay? And then looking at this impact that they may have, since we don't know how big these things will be, how frequently, etc., in particular, since we don't know how big it will be, we don't know how the cost will be. So we have no clue on actually estimating what this will do. And so, since it hasn't happened in the last 60 years, does not mean that it will never happen. So, but maybe I also should be critical about myself. Maybe I have been a neo-Luddite when stating in 1983 that what, at the time, the concept DCS, the acronym didn't exist. What I was looking at is basically an oil refinery, and I pointed out in 1983 that you can actually hack that by having access to the local area network, which when Honeywell came out, Honeywell Control came out with using Ethernet cable to actually control the computers and communicate with the computers on such an oil refinery. And an oil refinery are several square miles. What happens is that on this oil refinery, you will find public roads. You just can travel through and you will actually see sometimes these cables. And so at that time, even though there was no internet, you could actually hack this in and you could actually send incorrect control statements. And basically I made the claim that you might blow up such a plant without the need for explosives. Never happened. Never happened. So yeah, maybe I was also screaming and saying, careful with all this technology. But in the meanwhile, although there's never been a major disaster, Vitek Boden, who some of you may have heard about it, hacked a computerized sewage system in Queensland, Australia, showing the potential danger that actually could be done. So that's enough about do we need cryptography. So I think that by talking about basically credit cards, chip and pin, etc., that I hope that you're motivated, that it's actually useful. So what are the strengths of our modern research? And that's what basically, looking at the research in the future is going to be the main aspect of my talk. And so that's why I think we should look at what we have today. I think that proven security is a major success. It can be viewed, I think, as the biggest scientific success in cryptography. It was introduced by Shannon in 1949. And so I disagree with Jack Stern, who at Eurocrypt said that it was introduced by Rabin in 1979. And if you look at Shannon's paper, it has a definition of basically privacy. It says that the ciphertext should be independent. The probability of the ciphertext should be independent of the one of the message pair. And that is a definition. Okay? It's a very simple definition. It's not a long definition as we see today in most crypto papers. It's a very simple one. And there is actually a proof. So there is actually a theorem and a proof that the one-time path satisfies this definition. Adding the computational complexity, that was done by Rabin in 1979. And there he actually has a proof, but he doesn't have a proper definition. And so the paper was rejected, as we all know. And so basically the lesson is that if you're a student and you're writing a paper and your paper got rejected, don't necessarily panic. I mean, Rabin's paper has been cited many, many, many times. It still is a rejected paper, okay? So but one way we could look at it, I mean, we all know who one of the referees was and why it was rejected. But one way we could look at it from a scientific viewpoint is that it didn't have a good model. It doesn't actually define what it wants to do. And so, therefore, by not being very precise and saying what it can protect and not protect, then the chosen text attack broke actually the scheme. And so that's why I think that Goldwasser and Micali played a quite important role by actually putting a definition there. Same as Shannon did, putting a definition. And then they said this very, very narrow definition basically limits the attack to quite narrow, in a quite narrow sense. In that very narrow sense, under an assumption, they then proved that their scheme was secure. The assumption is still unproven, but that's unfortunately the only way that we can proceed today. And I think there have been some successful developments. And I'm going to take some that I played some role in myself actively, key distribution. So what you see in key distribution is that today, the community is able to design, prove and secure the key distribution schemes under some assumption that are actually practical. And similar things have actually been done for encryption. And so if you look at encryption, you can start with Vernam, which basically was unproven. And actually, if you look at, it was not yet called a one-time path, the idea of actually using it only once came afterwards. And that was 1926. Then Shannon in 1949 proved that the one-time path, when actually the one-time version of the Vernam scheme was actually the secure. Goldwasser and Micali introduced the notion of semantic security and had a proven secure scheme that achieved security, but it was extremely impractical. Nauer and Jung basically had a public key crypto system provably secure against lunchtime chosen ciphertext attack, and we had to wait until 1991, which is not that long compared to 1990, until there was actually, by Rakov and Simon, a scheme that was secure against all known types of chosen ciphertext attacks. Then what happened is that all these schemes were completely inefficient, and Kramer-Shoup was the first practical public key encryption scheme secure against CCA2. So why do I put quotes around practical? Because when you talk to practical people, they say this is not a practical scheme. They say it still needs so many more exponentiation than in the case of RSA or El-Gamal. They say, and that's why we don't want to use it. So Kramer and Shoup in 2002 formalized hybrid encryption and proposed a class of schemes. And more recently, Kurosawa and myself basically, and this just appeared a few weeks ago in the Journal of Cryptology, together with Gennaro and Shoup, who improved on our scheme, we basically showed that one can make an even more practical version of what was done earlier by Kramer and Schupp. So are we there at the moment? We're actually, yeah, we're getting closer and closer and closer to actually getting to proven secure hybrid encryption, which is practical. So that, I think, is a major success for the research. But I also think that we need to look at the shortcomings of our modern research. There are several problems, and they are from different natures. So I think we need to start looking at the foundations of modern cryptography. Are they fine? I don't think so. And why are they not fine? Because if you look at, so why did I pick the area of basically the encryption, in particular public key encryption, is that once you look from 1982 with the paper from Goldwasser and Micali, we have had quite a number of papers bringing it from a theoretical solution, very limited first. Goldwasser and Micali is very, very limited. And then theoretical solution in the early 90s, and then moving toward a more practical solution. But when you compare that to the research on conventional crypto, this is not happening. There is nobody today who is looking and saying, we are going to lay the foundations in conventional crypto so that in 30 years from now, we will have a block cipher which is kind of practical, maybe twice as slow as what will be designed at that time by heuristics. No, you go to these conferences as FSE, and they were basically all trying to break the scheme that came out just a few months ago or a few years ago, and they're trying to design a new one. That was what public key cryptography research was about in the 80s. Okay? And that has, except you will always find people who are 20 years behind, but that's basically what has stopped in public key cryptography research. But in conventional crypto, they're continuing with that. And so when you then look at hash functions, the situation is even worse, because with the attack from the Wang from China in 2004, it's kind of now, oops, which hash functions are still secure? MD4 went, MD5 went, SHA-1 went, etc. So we can't claim that everything is going well. And what people should start looking at is what assumptions do we have when we look at Boolean functions? Because what happens is we know how to build these things when you're going to use number theory, and then they become so slow and nobody ever sees that in 30 years we will have something which is basically twice as slow as the current block cipher at that time. So it seems that we have to look at Boolean functions. The problem with Boolean functions is we know worst case analysis, but nobody's looking at actually average cases, okay, as factoring and discrete log and this type of stuff that look promising. I know this is going to be, it has to be basically a long-term research. If we can do it in less than 30 years, evidently it will be really great. But why the heck is nobody working on this? Okay? And the impact is that by having practical hash functions broken, how can we say that the research on digital signatures is doing fine? So you see all these beautiful papers that are all up here, they all assume that you have basically a secure hash function. There have been people who have looked at truly proven secure digital signatures, but they are way too slow, and so nobody is even planning to use it, and we don't see how to make it fast in the next years. So I think that this is an important aspect that needs to be looked at. And I had a chat with the Quiz Quater, who basically agrees. He also thinks that the FSE community, basically the community that looks at conventional crypto, is on the wrong track. And also, if you look at hybrid encryption, since it relies, hybrid encryption says you're first going to start using with a public key, and then afterwards, once you have a session key, you will basically use a conventional crypto scheme. Also there, we have to rely on conventional crypto, and so a similar disaster should not be excluded. So I'm looking at, in blue, I know some of you may be colorblind, so we are at the level of foundations of modern cryptography. In there, we looked at lack of foundations for practical conventional cryptography, and now we're looking at incorrect security proofs. The most famous example is OAP, optimal asymmetric encryption padding. There are many, 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 many more examples. Okay, and there have been people estimating, saying maybe a quarter of the proofs have no bugs. It doesn't mean the theorem is false, but the proof has a bug, and some people say 50% of the proofs are fine. So we don't know, and very few people actually are checking these proofs, except for very famous papers. Then what we have today is questionable proof techniques. The random oracle, for example, we don't know whether it's really, when we have a proof under random oracle, whether we have truly security. So it's, to say the least, the security is questionable. And I also think that we another problem is the validity of our assumptions. So for 30 years, we have used RSA, discrete log, etc., etc. So many, many more problems that some of you may be familiar with or have heard about. So, but there are certain questions we need to ask about this validity of our old assumptions. How valid are these assumptions? It's a question, I think, which we don't know how to answer in the near future. But have we made any progress on finding some better upper bounds for the time it takes to break them? And any other comment, please? So the first is, it may take too long time. Basically, you're waiting for complexity theory people to make a major breakthrough, which may take a few hundred years or maybe 1,000 years. We don't know. So we just cannot wait for them. So, but then the question two becomes important. How have we made any progress? And the answer is really bad. It's almost none. The situation is truly bad. For example, the last time a major effort was made to develop a factoring algorithm was 20 years ago. There have been some improvements, I'm not saying that, but it's essentially today it's number field safe. And what does that mean? We're usually, so what we do when we talk about cryptography is that for the 20 years we have not evaluated the main principles of modern cryptography. And we claim to be high tech. I mean, talk to people who basically, that make laptops, and you say, oh, why don't you use stuff from 20 years ago? They are going to laugh at you. Okay? But that's what we as cryptographers do. We're using things that haven't been checked properly for 20 years. So this would be unacceptable in other areas, but we do it in our area. There are some positive notes. I'm not going to overstate. I'm trying to be giving a balanced talk. So there has been some work on proving equivalence between CDH and discrete log, for example, by Maurer. We also have this basically generic group model, which basically was generalized by Schupp in 1997. So I'm not saying that there has been no work, but it's definitely not enough compared to all the new schemes that are being made and proven secure. And it's kind of, what about the foundations, folks? What about the foundations? We don't look at those enough. And now another comment is that in the meanwhile, in particular Bonnet, every paper that's appeared by Bonnet almost has a new assumption. And why would they basically be secure? Okay, it's kind of, yeah, it looks, when you look at it, you in the first, if you look at it quickly, you don't see how to break it. Okay, but it may actually make the situation worse. And then the question is, what about the worst scenario where I have an invalid assumption? So Abdallah and Poincheval in 2005 had basically an invalid assumption. And their assumption was a one-page assumption. And so far I remember, it appeared at Financial Crypto 2005, where they had a regular paper. And then the assumption was broken by Zidlow of, if I remember correctly, RSA Corporation. And he got the short paper accepted. So everybody asked him, said, are you not upset? These guys, they get a full paper. And you only get a short paper. He said, no, because I could indeed explain in these few minutes that the assumption was false. It was kind of, you divide this by this, and boom, the whole thing goes. Kind of looking at it, forget about all these things, just look at this, and now numerator and denominator, they cancel, and finished. Okay? It was really, 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 really simple attack. So, the question is, from all the other assumptions that have been made, are people actually trying to break them? I don't know. Now, I'm not going to exaggerate, and I think we should definitely not rush the area of proven security, as for example done by Koblitz and Menezes. I actually think it's one of the strongest things that have happened in cryptography, but we should be at least aware of the situation. Okay? And so if you look at what has happened in the computer security community, they also have done lots of research, for example, on key distribution, and there they are still in the cycle of you make a scheme, you break a scheme, and then you basically are going to hack it, and you hope it cannot be broken. So while I think in the crypto community, there is something that we can be proud of, that we can design key distribution schemes that actually have proofs of security. So I don't think we should rush the area of proven security, and that's definitely not the goal of this talk. So the second issue, the other two issues, were basically the other issue at this level was foundation of modern cryptography. The next one at top level in future research is classification of practicality. Today we don't have that. So evidently you could say you have the class of the research that has been successful, but then there are also those that are basically considered practical, but in reality when you talk to practical people, they got very close, but not close enough to actually make the thing practical. And as some of you know, I worked quite a lot on threshold cryptography. And so in threshold cryptography, for those of you who are not familiar with that, is you just say, oh, this laptop, I don't trust this laptop. Maybe there's a bug in the Microsoft operating system. Maybe the hardware has a bug. And so you're going to say, I'm going to also want to rely not just on this platform, but I want to have another platform and possibly another platform, the one, for example, having an Intel, the other one Pentium, the other one having an AMD, the one running Windows, the other one running Linux, etc. And now, if I'm going to have to sign very important documents, so suppose the CEO of a company has to sign very important documents or very large the transactions, financial transactions, then you don't want to rely on the insecurity or the claimed security of a single platform. You will only be able to produce this digital signature when all this or a threshold of these the computers have actually been involved. And even if you can hack the security of less than a threshold, then you will still not be able to break the security. So you would think that this thing would be used widely, isn't it? The answer is no, it's not. Okay. So Shoup wrote a paper in 2000 in which he described the earlier work as much more complicated. And the earlier work was basically co-authored by me, so that's why I don't like Shoup's statement. And also states that in the previous work, the size of the individual signature share blows up linearly in the number of players, and gives his paper titled Practical Threshold Signatures. Now, King, who actually is an associate professor a little in Indiana, a little bit more south from here, in hisOctober 2000, he points out that the computations in the earlier work are actually much faster than in the, and that's for the case of passive adversary, than actually in Shoup's work. Okay? So it's amazing, isn't it? So it's not an improvement from the computational viewpoint. And Kramer-Fair, they presented a black box secret sharing scheme, which has an exponential improvement. So it brings down the size of the share to logarithmic what existed before. But unfortunately, if you look at it, the computational cost of running that scheme, it's enormous. So something might be from one aspect more efficient, but not from another one. Look at the modern the laptop today. How much disk space do you have on that? Massive, okay? So it's not because you have a scheme that the size of the shares get shorter, that therefore it's a better scheme from a practical viewpoint. So lots of things have improved on threshold crypto, but then it stopped and we are too far from being really practical. And so the consequences are that the Shoup scheme is being used, although there are other schemes that in certain circumstances will be faster. But it's only used in the top security level of, for example, credit card companies. They don't use it. And so when you talk to people at, for example, Swift, they don't use it. And even if you have large transactions, they just use ordinary RSA or variants of that. And so you have to be very careful with statements of practical when theoreticians actually claim that something is practical. It's not necessarily practical. So there we have something which got close to practical, but never got there. So you have practical work, which is actually, I think, irrelevant. So you could say it took more than 20 years before you actually before hybrid encryption, proven secure hybrid encryption, got to where it is today. So I have to basically make a disclaimer, okay? So I'm not going to say that it will never be used, etc., etc. But so I'm not going to make a statement saying this is definitely impractical, etc., it will never be used. What I'm going to say here are more question marks. So the question is, will the following claim practical research areas ever be widely deployed? Something as if you look at SSH and SSL, which is widely deployed. And the example is blind signatures. Charm concept of blind signatures is really nice. But where is it heavily used? Okay? I'm not saying that it's not used. There are few implementations. Undeniable signatures is newer, but any real-world applications? Not that I know. E-cash and e-auctions, yeah, I mean, Google is using that to some extent. So there are nice ideas there, but also not widely implemented. The next two categories are practical problems that have basically not been studied, and those I will look at later. And there are also the impractical ones that basically are too important to give up on. And in that category, I would put secure multi-party computation. So in threshold crypto, what happened there is, so threshold crypto is actually newer than secure multi-party computation. Secure multi-party computation is an older concept. So it's similar to threshold crypto. You don't trust your platforms, but instead now of calculating a digital signature, you basically want to compute a particular function in multiple inputs. And you don't trust the participants who actually are involved. They may actually lie, and they may actually behave very badly, etc. It's quite clear that this is important. As long as companies are not being able to bring us computers that we can say we can trust these computers, then we need to rely on having different platforms in order to get something more secure. The problem is that today this is very, 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 very far from practical. Now, if you talk to Ivan Damgaard, he will say, no, I have an application. And what's my application? So his application from Ivan Damgaard is that he now is using that in the sugar beet auctions. So in the United States, sugar is made from cane. In continental Europe, due to the blockade of Napoleon, I mean, it was the British blockade against Napoleon, they basically couldn't get the sugar cane. And so therefore they looked at beets, and they actually now start to select the beets that have more and more sugar, and today that's still being used to make sugar. And they use a very complex auctions in which the farmers try to get as much money, and the ones basically who are going to make the factories that are going to extract the sugar from it, they're basically trying to pay as little as possible. And so then they don't have to agree, they have to go in another meeting, etc. And usually this thing takes a month, okay, of negotiations where farmers put prices and then the industry put prices, and then they say, okay, there's no match, let's start over. Now you know what these guys are willing to pay, and you know what the farmers want, let's start over, and then they continue, and after a month they get to a price which is acceptable. Imagine going to, for example, Sotheby and buying a painting. It takes a month before the seller and the buyer agree. That's not done, okay? But yeah, in the sugar beet industry in Denmark, this is done. So then they implemented that, and now it takes several hours of computers. Okay, for that application, it's fine. It's faster than what usually happens. But now imagine doing that for everything that you go on sale on the internet. No way, okay? No, nobody wants to do that and taking hours to do. So, but except for very few applications, it is really impractical, and we should really try to bring it more practical. And the reason is not that it looks quite interesting from an academic viewpoint. No, I think there's a fundamental reason why we need to continue doing research in that area. So what should be studied? So first of all, everything from above. You can look at what I mentioned, and then you can basically conclude. And I'm just going to give some examples. Invalidations or validations of our assumptions, I think, is very important. Now, how could we proceed? So the way that I think some people could proceed is, so first, it's known that if discrete logarithm would be easy, then computational Diffie-Hellman would be easy. And if this and computational Diffie-Hellman would be easy, then decisional Diffie-Hellman would be easy. And there is something else that Maurer introduced, which he called the decisional square Diffie-Hellman. And so there what you have, you're going to have an alpha and a beta, which beta is alpha to x. Then you're going to have a gamma. And the question is gamma equal to alpha to x to the power 2? It's kind of similar to the decisional Diffie-Hellman, but then having basically instead of an x here and a y, you have twice x. And so if this is easy, then this is obviously easy. And so what I think we should do is we basically are stuck. We don't even know how to prove that. But maybe what we should do is try to make something which looks easier. Okay? So find a hierarchy of problems that all seem easier than the decisional square Diffie-Hellman. Until you get so low that you have something that one can prove to be actually easy in a not too trivial way. Okay? You don't want to go so low that basically there's nothing to be proven anymore. And then the insight that you have by understanding that this problem, that first of all, when you write it down looks easy is not, then try to go back up and say, can we then prove something about the easiness of the problem above? So how far can you actually collapse this hierarchy? Okay, that's a possible approach. So another thing is verification tools for our proofs. How many people are working on that? I only know one paper that appeared at Crypto, where a bunch of French researchers from ENS, they actually looked at the very, very narrow context of group key distribution, and then they made an automatic tool to actually make proofs. Okay? But it's very little. By having basically estimated something between 50 and 75% of the proofs being correct, then we need some tools to actually check whether these proofs are good. Some researchers in formal methods claim that they could make progress on this. Some have actually looked at it. I spoke to a guy from France who actually looked at it and he gave up. So, but we cannot just continue this way and just having papers accepted primarily at conferences and even in some cases journals, and then basically find out that there was a bug in, and many of them nobody ever looked at, and basically maybe somebody will never look at it. It doesn't mean that they will not be used. That's the bad thing. So I also think that we need to do research on reducing the gap between theoretical and practical, in particularly when you have come so far, kind of now stopped. Can we not push this closer? So that's a question. Now on the high level of what research topics we should look at, I think that there are enough problems in computer security that are not being looked at by cryptographers. So one can almost say that except for secure multi-party computation, cryptography today by researchers in cryptography is still being viewed as communication security. And why the heck would that be? I don't see a reason for that. I mean, when you look, we came from privacy and then authenticity, etc. Why would we stop at communication security? And so an issue is that we evidently may have to adapt some of the problems so that they become easy to study. And so, for example, one question is, can we make proven secure operating systems? Now, everybody, in particular people who are working on computer security, are going to say, this is way too hard. Now, wait a moment. If you look at Rabin's paper, and if you look at Goldwasser and Michale, they had security defined in a very, very narrow way. Okay? And they had then some scheme which was completely impractical. So I'm not saying a practical operating system. I'm not saying secure against everything. I'm saying something very narrow and very slow. Okay? And then in so many years' time, let's extend basically what the security definition means, and then make it more practical. So far I know nobody's working on that in the crypto community. Proven database security. There are some people, cryptographers, who have looked at certain aspects of the database security, but there are other problems that actually should be looked at, and I'm just going to give one example from inference. There are more examples. If you start to think about it, there are many more examples. And this example is actually coming from Denning's book, The Cold War. It's a Cold War example. So what she writes in her book is that the Rand Incorporation modified during the Cold War maps so that the Soviets could not use them to find the exact location of strategic positions in the United States. And what it does after the transformation is that with a not too bad accuracy, you can actually measure the distance between two places. But using these maps to accurately know where something is located is not. Now, evidently now with satellites, etc., and GPS, all these things is useless. But it's a nice example. And so when you think about this in the context of AIS, so you remember this boat story, then you can think about broadcast encryption with asymmetric trust in the receiver. That means that if you basically are a ship nearby another ship, you should know where that other ship is to avoid a collision. Okay? So there you are trusted. But if you are farther away, as for example, you have a container on that ship, and you know it's going to take a week anyway, or maybe more, before your ship is going to arrive, why the heck do you have to know the exact position of that ship? There is no need for that. Okay? So you have an asymmetric trust in the receiver. And so that means that depending on your need, the need to know, you will actually get the data, but quite inaccurate. So you may know that except if there's a major storm or something, that your ship is expected to arrive that day. And the closer it gets to the port, the more precisely you will know when your container is going to arrive. So that's basically inspired by Tenning's book, and it's quite nice. It's basically coming from the computer security, but then actually looking at it from a crypto. So nobody that I know actually has looked into this aspect. So I was told to finish at aim for 5:20. It's now 5:22, so it's time to conclude. So although cryptography is not perfect and may not have prevented catastrophes so far, there are plenty of examples that demonstrate its importance. The academic research has flourished to a degree never anticipated by pioneers as Diffie. So I heard not too long ago a talk by Diffie in which he said somebody would have asked him in 1976, are you going ever to imagine that there will be a call from NIST for making block ciphers, and that's not a call to basically NSA, but a call to the academic community, and then have a bunch of Europeans design it and become a standard in the United States. And not just a standard, but actually being approved for the use of the encryption of top secret data in the United States. So I think that this is a major success for the research. And other examples include modes of operations that also were designed by academia. So there have definitely been successes. So some proven secure crypto systems are truly practical, and other ones get close. So I also think that's quite a success. So overall, I think that the research in crypto is actually in good shape. However, some redirection should be considered within the community. And for those of you who are young researchers, I think it's quite exciting, in particular when you like discrete math and complexity theory, to actually apply it in crypto. But I think you should look at the following advice. I think you should spend 20% or 30% of your time trying to break assumptions. Okay? Because if nobody's going to do it, in particular the young people aren't going to do it, then what happens? The situation will get worse and worse and worse. Now I didn't say 50% or 60%, okay? So, but now if you make progress, then your advisor might say, oh, wait a moment. Yeah, you should really, really continue on that. That's actually much better than everything else that you were doing. Why don't you make your thesis from what you've been doing? But that's only after you make your progress. So it's kind of, you're spending some time in case. Now the probability something will come out is kind of estimated to be low, but you never know that you're lucky. The payoff would actually be great. I also think that you shouldn't trust theoreticians when they say something is practical. Okay? And so, I'm particularly looking at research that turned idealist. I'm not going to mention names, but some people have been looking at practical issues from the ivory tower instead of originating from actually real need. And I think we need to look at balancing. What do we really need? And are we going to continue on making more and more and more papers on topics that so far look never going to be implemented? And so besides considering the classical problems, consider some not so well studied topics that might actually be more relevant. And so finally, I would like to say that proven security is exciting. It is really exciting, but it's very easy to make mistakes. And I will tell you that basically the paper that appeared in the 2008, if my memory is correct, with my co-author, was going to appear in the IEEE Transactional Information Theory, had a bug. And that bug was found after the acceptance of the journal paper. But the galleys were not out yet, and so we actually stopped. We asked the editor to stop this paper. Lucky enough, my co-author could sort out the bug. But I think we have to be honest. I think we as cryptographers have to be honest. Making proofs is hard, okay? And it's actually a student of me who designed a protocol for some generalization of what that was going to appear in IEEE transactions on information theory. And I broke his scheme. And he said, oh, you know, if you can break my scheme, I can break your scheme. And so then he showed me, and so basically, he was right. We were lucky that we could fix it. So it is indeed very, very hard. And many, many people have made the mistakes. And I think we should be basically honest and saying, be very, 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 very careful. Check every statement. And when you have longer and longer proofs, which in particularly are encouraged in the complexity community, if you have a paper with basically the proof is too easy, too convincing that it is correct, then it's kind of, yeah, this is too easy, let's reject this. But what people have to realize is that the longer and longer the proofs are, the more and more complex the protocols, the more and more complex checking that these things are correct. And so, should we accept papers that have long proofs? I'm not so sure of that. I think that sometimes people need to think about trying to make the proof shorter. Now, I know that the proof of Fermat's last theorem was quite long, etc. But what happened there is that they basically very, very, very carefully checked it. And they, as you know, a bug was also found in that proof, and then the authors had to restart. So we shouldn't be, we have to be careful. That's basically my conclusion. Any questions?
Well, I'll make a comment, and this is something I've been talking about for a few years. One of the problems we have, and it's not simply in cryptography, but across much of computing, our reward system has skewed what research is all about. So we have a system whereby funding goes to those who can solve problems that are needed right away. The solutions are needed right away. So government does that, companies do that. Instead of promoting longer term, more fundamental research, we want to see the results right away. They're not willing to fund research that produces negative results. And so
that's what it used to be in Europe 10 years ago, by the way.
And so we've gotten to the point where we're very conservative in the kinds of things that we're willing to propose. We also see in the arena of publications that there's greater and greater competition to have higher rankings or better publication rates. And so we see more and more papers with less impressive results. And as a field of computing in general, we don't really encourage or reward negative results or attempts to reconfirm what others have done. In the biological sciences or physical sciences, they redo experiments to show. We don't do that because there's no publication in it, and there's no money, no one will fund it. And so we've developed a discipline that increasingly is more and more ad hoc results that look good at first blush, and then nobody looks back because there's no reward for it. So I agree with you completely, but I would say it's actually a much broader problem than simply
But there are
cryptography.
approaches. I mean, when you think about the internet, there are approaches that we could consider as, for example, making a database. It's not the first time that I thought about, that I basically spoke about using databases to look at all the schemes, protocols, etc. that have been developed and make it available on the internet. But it was a different context. It was in the context of actually checking whether some scheme that is being now proposed is actually more complex than a trivial combination of existing schemes. But that same database could be used to relate it to your question, where people basically say, I taught this proof in my class, okay? And I have answered all the questions of the students, and so yes, I'm going to tick that I actually taught this proof in my class. It means that somebody has actually looked at it, talked about it quite in details, and then having the possibility of students who say, I don't understand that, oops, that's a bug, okay? So I remember when I was in Montreal, I actually was teaching students about the Fiat-Shamir protocol for identification, and then some student in the class actually mentioned that some attack against that scheme, which then became a paper at Crypto. So that would be one solution, and this is not necessarily limited only to this area. It might be done in broader context, where people basically attach their name saying this has been verified. Not necessarily say that it's kind of a trust, building up a trust system. It doesn't necessarily say that it is good. And I do realize that also formal methods are limited. it's kind of a little bit when you look and you talk to electrical engineer. They design circuits so that they become easier to verify. And that's also an approach. But yeah, the funding is a big problem. And I heard that National Science Foundation has been basically clobbered. And that goes back to the Bush administration. And that's actually very, very sad.
And earlier.
And earlier, yeah.
One of the problems with anything that pertains to security, be it cryptography, be it system security, be it even national defense, is societal credit is often. How do you claim credit? How do you get credit for what did not occur?
I used to have on my slides, a citation to somebody who, and then I said, oops, I put this guy's personal citation on my slides and I haven't asked him his permission. And so I've emailed him and he didn't basically want this citation as, actually he had told me. And so then I removed it, which is really sad. So what happened to him, I'm not going to mention his name, I'm not going to mention the company. So it was a company that in the 80s invested a lot of money in actually using authentication to make sure that people who actually going from outside the network and trying to go in, that they're actually authorized. And so they used DES and other techniques at that time in order to guarantee the authenticity. So this company became in financial problems in the 90s. And they called the head of this group saying, okay, you have basically recommended us to implement all this crypto. How much did you actually save? And so when I teach about intrusion detection, I say this intrusion detection thing, although it's quite limited, is useful because then you can actually use it. I actually spoke about it with actually mentioning his name about intrusion detection and when you look at how much money has been saved. And that is the issue. And so he lost, not only did he lose his job, but the whole group was fired because he couldn't demonstrate how much money the company had saved. So yes, this is an important aspect. And that's why I think it's sad that I can actually not mention the name, his name, and the name of the organization for which he worked, and actually state what you exactly said. Yes, yes, it is. You know, there are people looking at economic aspects of security, and so that's an issue that should be definitely there.